If you want to see this in the calculator, what you would do is go back into the distributions, like in chapter 4, so second vars for distributions. In this case, we'll pick normal CDF, and we have these inputs here, the lower boundary, upper boundary, mean, and standard deviation, where it defaults to having a lower boundary of -1 E99, which is to say a -1 followed by 99 zeros, and a possibly large negative number to say we're going to go off as far as we possibly need to in that tail, and then a little bit farther to still, just to be sure. Then the upper boundary is how high we're going to go, where in this case we're going up to 1.15. So the calculator is defaulting to working with accumulations up to a point. It's defaulting to working with CDFs as they're kind of designed, but we can adjust that if we need to go above, which we'll see later. And then from there, because we want the standard normal, we want mean mu equals 0 and standard deviation sigma equals 1. So again, calculator defaults to that, and we'll make it run, where we get the desired decimal up to 4 decimal places of specificity. On the other hand, if we want to find the area between two z-scores, it's not actually that different. So first, second vars for distributions, normal CDF, where now our lower boundary is not some stand-in for the largest negative value we can come up with. It is specifically -1.5, and our upper boundary here is 1.25. Put those numbers in, and you make it run to get a value of about 0.8276. Let's say that we want to do something where we're finding an area between. Again, if we want to, we can convert everything that we work with to being in terms of z-scores and use standard normal distribution properties, use standard normal distribution probabilities. But really the only difference between a standard normal curve and a general normal curve is a matter of shape and is a matter of scale and position. The shape, most importantly, is fundamentally the same, and the probabilities, up to rounding, are precisely the same. So, in terms of what we're trying to look for here, it doesn't actually make a difference, depending on how we want to approach the problem anyway. But for this, what we can do is go into our normal CDF, put in the lower bound here of 22, the upper bound of 52, with a mean, in this case, of mu equals 43, and we'll get the standard deviation, sigma, in this case, is 12. Put all those in there, make it run, and as you can see, up to specificity we get the same answer. Where, if you wanted to run that without those interface options, we wouldn't be changing all that much, but we might as well see how to do that at least once. What you would do is go into CDF, put in the right lower boundary, 22, comma the upper boundary, 52, comma the mean of 43, and then finally the standard deviation, which here is 12. And we get the same number, essentially. So here, again, we can talk about this in terms of the normal table, but there's really no reason to. What we're going to do is go in here, normal CDF, yet again, and now we have a lower boundary of 37, which we could convert to a z-score of -1.5, but, -0.5, gotta be careful, and then find a complement. Or we could go directly in the calculator, make our upper boundary some large number. I'll use the standard 1E99 so you can see how to do that once, but really anything big works here. Just be aware of how big the values we're looking at in terms of our distribution are, but put something big in there. We have the same mean, same standard deviation, run it, and we get that our probability here is roughly the same, about 69.14, where you can use that to say something else about the overall amount of things in our distribution. Here, the amount of people in terms of the amount of time spent. But it's a specific thing for this specific distribution. It works similarly for other distributions with other values. Now for this first problem, we want to find the z-score that corresponds to a cumulative area of 0.3632. And to do this, we go into our distributions, so second vars, and scroll down to our third option here, inverse normal. This is the function for specifically finding values given areas to the left. And that's important that this function only works for areas to the left. But anyway, we get this. And here we have our values, where we get the area, in this case to the left, is 0.3632, and we want a z-score, importantly here, where because we want a z-score, that means we want the mean mu to be 0 and the standard deviation sigma to be 1. Paste that. If you don't have that menu popping up, you do inverse normal, 3632, comma 0, comma 1. Run that number, and we get our z-score approximately. For our last bit here, we're going to look, instead of talking about z-scores, how these things work for general distributions. What you really want to do here is understand that the inverse normal function actually works just as well for this, it's just not what it's defaulting to. If you want to work it with that, what you would do is get into inverse normal, and in here, because you have top 10%, that means you want 90% to the left. And 90% to the left, like I said, 1.28 is a pretty common value. It's one to know, but we're going to pretend we don't know that. We have 0.9, and even if we do know that, we don't know how it fits for our perfect distribution, as it is perfect. Normal. Non-standard. It's not perfect by any means. But we have that mean of 50, and the standard deviation here is not 1, the standard deviation is 10. So instead of doing this work here with the estimation and the z-score and then the conversion, we make the calculator do all the work for us. And then we get our answer. What we're going to do is recognize our values here. So we're going to go second vars for distributions and go back into normal CDF, where now we have a lower boundary of 19.4, an upper boundary of 22.5, and here the mean that we're looking for is really a mean of sample means, mu sub x bar. Can't tell the calculator to specifically look at that, but mu is close enough for the case for what we need. So we're going to say the mean is 20.7, just bearing in mind that that's actually a mean of sample means, at least in this case. And for sigma, the standard deviation, it's not enough to just take the value of 6.5 here, and the reason for that is when we're talking about the behavior of a mean, because a mean takes into account usually many values, in this case 50 values, we want to notate the fact that it has a lot less variation than just the single value. So instead of the standard deviation 6.5, we divide by the square root of the sample size 50 to get the standard error. But again, the calculator doesn't say that's sigma sub x bar, it just says it's sigma. We just have to bear that in the back of our minds. Which is about 0.9, but when we put it in the calculator, we can be a little bit more exact. When we're making a 95% confidence interval, that means we have 95% in this middle region. So we're going to have 5% split between the tails into 2.5s. And if we want to represent the value there to get those scores, what we're going to have to do is go into the calculator and use the inverse normal computation for this, where the area we want, if we want the low end, the negative value, we can use that 0.025 with an area to the left, or if we have a more advanced calculator, we can do 0.05 with the area to the right. But what most of you are probably going to do is put in 0.975 for the 95 in the middle and the 2.5 on that left tail to find this value here of 1.96. Using the calculator, with some room for rounding. To compute this in the calculator, what we do is go into second distributions, and if you have the 84 or above, you'll have the inverse t computation. But if you have an earlier calculator, you won't have this option. So just be careful with that. But if you have this, go ahead and put that in there, where he would have 0.975 and 14 degrees of freedom, getting about 2.145, where this computation is a little bit slower because it has to be a little bit more picky than with the normal distribution. Now we can do this more or less by hand, setting up all of these pieces where you have to get that critical value, as it were, and sometimes in the homework they'll ask for all these steps here and then get the margin of error, or add and subtract and get the interval. Or we can see I do this in the calculator using the t-interval computation. So for that, you hit stat and then scroll over to tests, where from there we go down to t-interval. Looks like it says tinterval there. And we're going to make sure that we have the stats option selected. The nice thing here is with the 83 and the 84, I think the menu is basically the same. And in here, we're going to put in that mean value, x bar is 22.9. The value for S is 1.5. And our, I want to put a plus sign in there. I hit the wrong button, should hit enter. The sample size is 20, which means we have 19 degrees of freedom if you prefer. And we're working for this with a, just to be sure, 90% confidence level. And as a result, it's going to run its numbers. It takes a little bit longer for the t stuff because the t's take a little bit more subtlety, but we will get our interval. What we're going to do is go into the calculator, and let me scroll back up here to make sure I have the right numbers, because being careful here matters. We're going to hit stat, tests, and we're going to scroll down here until we get to the 1 proportion z interval. It's not really a test, but construction. 1 prop zint, as it were. We don't really do much with proportions and t stuff because we get to use the normal distribution when we have appropriately large things, which here we have quite a lot of them. So in here, x is going to be the number of successes, that's 1054, and n is the sample, 1550. Once we have these values in here, if we don't want to do this computation by hand, which we generally don't, just run in the calculator and we get our numbers. So for this, we have to be very careful about pulling in all of the information that we're given here and what exactly we're looking for, because we want to see if the cost has gone down. That is our alternate, which we make first, and our null is that it has either not changed or gone up. So when we're going to go in here, we're going to hit stat, go to tests, and since we know the deviation sigma, we're going to use the z-test, where we have stats in this case. We are told that mu naught, the supposed parameter, is 835. Sigma, in this case, is 53, and we're comparing it to a mean x bar of 809 with a sample size of 37, where we're sure that we can use the central limit theorem for both reasons in this case, because it is both approximately normal to begin with and a large enough sample. Now from here, we are making the comparison that we have a smaller value here. That is, we're taking a left-tailed test. So we select that option here, the mu is less than mu naught option, and calculate, where for here we get our z-score as well as our p-value. Now if we want to do a test using a critical region, which I'll show an example of as well in here, we would have to compare this z-score to the minimum fitting that 1% level, but since we're going to work using p-values instead, we'll see that the p-value here is right there, just a little bit less, so it's inside of our rejection region, and as a result, we can reject the null hypothesis in this case. For us, the big things we should pay attention to here are that we're given a sample of 14 used cars that had a mean price of $19,189 and a standard deviation of 2950, where we are going to test this claim for level of significance alpha equals 5%, where we know we're using the t-distribution for this because we are only told information about the sample. We're only given a sample mean, and that 2950 is specifically the standard deviation for those 14 cars. That is an S value, not a sigma. So when we're going to be testing these hypotheses, we are going to test them using the t-distribution because we do not know the population standard deviation. And from here, it's a little bit more efficient to use the t-test computation directly, where what we're going to do is go in here. We have statistics. In this case, I'm going to scroll back up to make sure I have all of them properly, where the mean that we are testing is 21,000. The mean of our sample is 19,189. The standard deviation is 2950. And our sample size here is 14. Where when we make this determination about mu not equals less than greater than, that's in terms of our alternative. We're here, we're looking for a left tail, we are looking for less than. And if we want to see this, you can see that we get, up to rounding, the appropriate t-score. And then if we want to find the p-value, we can use the tcdf function. It's very rarely seen, but really we're better served going with this t-test computation. In any case, we get the appropriate values here, where we have that the p-value is less than alpha in this case, or if we want to be sure, we can also get the critical value here, where because we are looking for a t-score associated to 5% in the left tail, that level of significance 5% down there, and we have 13 degrees of freedom, that would end up giving us a critical value of -1.77 approximately, where because our t-score is less than the critical value and we are using a left tail, it is in the rejection region, and therefore we have enough evidence to reject the null hypothesis. In this case, that means rejecting the claim. What we're going to do is hit Stat, and then go over to Tests, and select option number 5, where that's what's called the one proportion z-test, one prop z-test, if you want to jumble that into one sort of word. We'll click on this. We have to be careful about our inputs here. We don't have as many, kind of like how with the one proportion z interval we had fewer options. Same thing with the z-test. Here we're going to put in the value for p-naught. We put this in as a proportion, where here we're talking about the research that shows 45% have saved money. So this value for p-naught is going to be that given 0.45. Meanwhile, when we look at the values from our sample, we represent this as a number of successes along with a number of trials. Where here we had 41% out of 100, so that will be 41 successes in 100 trials. And in particular, we are looking to see whether the percentage is lower than that supposed parameter of 45. So we are going to run a left-tailed test, select the left-tailed option, and then we will calculate. Where if we run that computation, we get from this our z-score of -0.80, where we have attached the p-value of 0.21. So if you want to think about this in terms of a p-value approach, we can see that the p-value is considerably larger than alpha, so we would say that we cannot reject the null hypothesis. Or if we want to be sure, we can get our critical value here, where that would be something with an inverse normal computation. Since we are looking for the 1% in the left tail, that'd be 0.01, and we would run this to get a value of negative 2.33, where we can see that with this left tail, the critical value is well below our test statistic. That is, our test statistic is not in the rejection region, so for that reason as well, we would fail to reject the null hypothesis and say there's not enough evidence to support the claim.